In this video, I want to take a look at the graphs of the solutions to these forced vibration problems. Now, in the previous video, we figured out the formulas for instance, the amplitude of the steady state solution. And what I have here is the solution typed into Mathematica. Now, I'm assuming that K is equal to, so the spring constant is 3. I'm going to let the gamma be variable, so that's the damping, and I'm assuming mass of 1. And so here's the homogeneous part of the solution, the exponential plus the cosine and the sine, and then the rest of this is in the previous video what I called A times cos omega t and B times sine omega t. Of course, I'm using x here instead of t, and I'm allowing various things to be manipulated here. So the damping can be manipulated. The omega, which is the period of the forcing function, can be manipulated. The amplitude of the forcing function can be manipulated, and then just some settings of my graph. Where do you want to? How much of the graph do you want to see? Okay. So that's changing the y's or the x's or the y's. Now, first of all, I have this currently set with gamma equal to 0, so there's no damping. And because of that, the transient part of the solution doesn't go away. It's not transient. It sticks around. So you see this sort of odd graph forever. Right? However, if there is damping, you would see that what happens as I increase the damping, you can see that the weirdness of the initial conditions and the homogeneous part of the solution goes away, and you end up with just that steady state cosine curve or sine curve that is the particular solution. Okay. Likewise, if I were to take the amplitude of the forcing function and bring that down to 0, then what you're seeing is just the transient part of the solution, which with no damping is just a sine curve or a cosine curve. But when there is damping, you have this decaying exponential. So when you have both damping and some amplitude on there, then you've got this typical forced vibration situation. Okay. Now, a couple of things to notice. One of the things is that changing the amplitude of the forced vibration doesn't really change the output dramatically. Yeah, it makes it a little taller or shorter, but it doesn't change the flavor of it. However, changing the frequency of the forcing function has substantial change, particularly in one spot where all of a sudden, wow, it gets really big. But I'm not changing the amount of gravity. I'm not changing the amount of spring strength. I'm just nor am I changing the strength of the forcing function. I'm just changing the period of the forcing function. And there's a spot where we hit what's called resonance. Now, in the math video, we saw that the resonance should happen right around where omega equals the square root of k. Well, k here is 3, and so the square root of 3 is 1.732. You should think George Washington, of course, with the square root of 3, because George Washington was born in 1732. So watch the value. You can see the value of omega right here as I'm changing it. It's right there at, well, it's hard to see where the top is because I can't. And so I'm going to vary this. Let me see a little more here. When I get into 1 point, yeah, right in here, it's where it's at its highest point, right around that 1.732 range. Yeah, at this point, I have resonance. Now I can change the amount of resistance, the amount of damping, and that changes what that highest point is. But still, even with a lot of damping, that resonance point is where you see the strongest output. And it all comes down to this k minus w squared in the denominator. So when W, or omega, is close to the square root of k, that denominator gets small and the output of the steady state solution gets large. The other thing I want to take a look at are the beats. When there's no damping, right, and the forcing function and the natural frequency are close together, you see these beats, right? However, when there's damping, the transient part of the solution goes away, and so you see the beats initially, but then not after time. So as I increase the the damping here, you can see that over on this end of the graph, there's not very much for beats, but yet there's still a little bit of a beat here. So the beats are not as big a deal when you have damping because you're not really adding the two cosine curves together, because one of the curves just goes away and you're just seeing the other one. But when the damping is small, you will see the beats, at least to begin with. Okay. And one last thing I want to point out, that resonance was happening at when omega was the square root of k. I have here k equals 3. If I change this whole thing to, let's say, k equals 4, then the resonance isn't happening at 1.732. It should be happening around 2. So what I see now is that, sure enough, I get that big response right there. You can see right when I'm at about 2. Okay, and again, it doesn't matter whether I have a lot or a little bit of resistance damping. That biggest thing happens right around 2. Okay, so there you go. There's the graphs of these solutions to forced vibrations.